August 19, 1944. Kugelbake Peninsula, Germany. The damaged Lockheed P-38 Lightning trailing smoke from its starboard engine was barely under control. First Lieutenant Albert Freeman of the 474th Fighter Group fought the controls as altitude bled away over the North Sea. His wingmen had already turned back, ammunition exhausted, leaving Freeman alone with dying engines and vanishing options. Behind him lay Allied territory, safety, debriefing rooms, and hot coffee. Ahead stretched German-occupied coastline, flak batteries, and certain capture. The port engine coughed, shuddered, and seized completely. Freeman had perhaps 90 seconds before both engines failed entirely and the Lightning became a 17,000-pound glider with the aerodynamic properties of a streamlined brick. He made his choice. Freeman aimed for what appeared to be a flat beach, dropped landing gear despite knowing it would increase drag, and committed to the emergency landing. The P-38's twin booms touched sand simultaneously in a surprisingly gentle belly landing that threw up clouds of grit but left the airframe largely intact. Before Freeman could unbuckle his harness, German coastal defense troops surrounded the aircraft, rifles leveled at the cockpit. The war was over for Albert Freeman. For German aviation intelligence, it had just become considerably more complicated. What German engineers discovered when they examined Freeman's P-38J would confirm suspicions that had been building throughout 1944. American aviation technology had not merely caught up to German designs. In specific critical areas, particularly in systems integration and manufacturing philosophy, American aircraft reflected an entirely different understanding of modern aerial warfare's requirements. The P-38 Lightning represented American engineering at its most distinctive, unconventional design, immense complexity, and absolute confidence that industrial capacity could overcome any technical challenge. Over the following months, as Luftwaffe evaluation teams systematically tested the captured Lightning, they would document capabilities that seemed almost deliberately designed to exploit German weaknesses. But more troubling than any specific technical advantage was the implicit message embedded in every system, every component, every manufacturing detail. America was building weapons without compromise, without substitution, without the desperate improvisations that characterized late-war German production. The industrial gap separating the combatants had become an unbridgeable chasm. The Lockheed P-38 Lightning had been confounding German pilots since late 1942 when the twin-engine fighter began appearing over North Africa. Initial Luftwaffe combat reports reflected genuine confusion about how to classify the strange American aircraft. It was simultaneously a heavy fighter with firepower rivaling twin-engine destroyers, yet it maneuvered with surprising agility for its size. It climbed rapidly to altitudes where German single-engine fighters struggled. Most disturbingly, damaged P-38s continued fighting with one engine completely destroyed, limping home on the remaining power plant while equivalent damage would have sent any German single-engine fighter straight down. German intelligence analysts studied gun camera footage and debriefed pilots returning from encounters with the Lightning. The tactical picture that emerged was deeply troubling. At altitudes above 25,000 feet, the P-38 outperformed everything in Luftwaffe inventory except the latest variants of the Focke-Wulf Ta-152, which existed in such limited numbers that they barely affected combat statistics. The twin Allison V-1710 engines, each equipped with turbochargers, maintained full rated power at altitudes where German engines gasped for oxygen and lost 70% of sea-level performance. The Lightning's concentrated nose armament, one 20mm cannon and 4.50 caliber machine guns firing through the propeller hub without synchronization delays, delivered devastating firepower without the convergence problems that plagued wing-mounted guns. The counter-rotating propellers eliminated torque effects that made German fighters difficult to control during takeoff and landing. But theoretical understanding based on combat observations differed fundamentally from detailed technical examination of actual hardware. When Freeman's intact P-38J was secured by German forces, arrangements were immediately made to transport the aircraft to Rechlin, the Luftwaffe's premier testing and evaluation facility. The Lightning received German markings, the characteristic yellow undersurface as preventing friendly fire, and the designation code T9 plus GK identifying it as property of the Zircus Rosarius Evaluation Unit. The assignment to conduct initial flight testing fell to Hans Werner Lurk, the same methodical test pilot who had evaluated captured P-47 Thunderbolts, Mustangs, and virtually every other Allied type that fell into German hands. Lurk approached the P-38 with professional respect tempered by wariness. The aircraft's unusual configuration, twin engines mounted on extended booms with the cockpit housed in a central nacelle, created unique handling characteristics that required careful familiarization. His first impression upon climbing into the cockpit reinforced concerns about American design complexity. The instrument panel seemed designed for an airliner rather than a fighter, with gauge clusters monitoring dual-engine systems, turbocharger operations, intercooler functions, and fuel management across multiple tanks. German fighters used simpler systems that placed greater workload on pilots through manual management. The P-38 automated numerous functions through interconnected systems that reduced pilot workload but increased mechanical complexity dramatically. Lurk spent considerable time on the ground studying controls before attempting engine start. The procedure for initializing twin turbocharged Allison engines without operational manuals required systematic experimentation and mechanical intuition developed through years of test flying unfamiliar aircraft. Each engine required its own startup sequence, its own monitoring, its own management. When both V-1710 engines finally rumbled to life, they produced a distinctive sound utterly unlike German inline engines. These were liquid-cooled 12-cylinder engines, each displacing 1,710 cubic inches and producing 1,425 horsepower at war emergency power with turbocharger boost. For comparison, the Daimler-Benz DB605 that powered the Messerschmitt Bf 109G displaced 1,475 cubic inches and produced between 1,475 and 1,800 horsepower depending on variant and boost settings. The Allison engines produced comparable power but did so while maintaining full output at far higher altitudes through turbocharger technology. Lurk taxied carefully, feeling the unusual weight distribution through nose-wheel steering. The tricycle landing gear configuration was still relatively novel in 1944, particularly for single-seat fighters. German pilots trained exclusively on conventional tail-dragger configurations found tricycle gear counterintuitive initially, though it offered significant advantages in visibility during ground operations and reduced likelihood of ground loops during landing. The P-38J weighed approximately 12,800 pounds empty and approached 17,500 pounds at maximum loaded weight. This made it considerably heavier than German single-engine fighters but lighter than most twin-engine types despite comparable or superior performance. The weight efficiency reflected American advances in aluminum alloys and structural design that German metallurgists noted with professional interest during later detailed examination. Lurk advanced both throttles for takeoff and immediately noticed the P-38's unique handling characteristics. Counter-rotating propellers, left engine turning opposite to right engine, eliminated the asymmetric torque effects that made high-powered single-engine fighters difficult to control during takeoff. The Lightning accelerated smoothly down the runway with no tendency to weather vane or require corrective rudder input. Rotation was gentle, visibility excellent, and climb rate immediately impressive. But Lurk's test plan called for methodical exploration of the flight envelope starting at lower altitudes where German fighters held theoretical advantages. Below 15,000 feet, the P-38 handled well enough but showed no particular superiority over contemporary German designs. Turn radius was adequate but not exceptional. Roll rate was moderate. Acceleration was reasonable. Nothing suggested the aircraft deserved its fearsome reputation among Luftwaffe pilots who had fought Lightnings at higher altitudes. Then Lurk climbed through 20,000 feet and the character of the aircraft began changing. The turbochargers, driven by exhaust gases and becoming increasingly efficient as atmospheric pressure decreased, forced massive quantities of compressed air into engine cylinders. While German engines lost power as altitude increased and air density dropped, the Allison V-1710s maintained full rated output. At 25,000 feet, Lurk pushed the throttles forward and felt acceleration that bordered on violence. The P-38 leaped forward with authority no German piston fighter could match at that altitude. He rolled into a climb and watched airspeed hold steady as altitude increased rapidly. Service ceiling specifications claimed 44,000 feet maximum altitude. German interceptors rarely operated effectively above 36,000 feet. The implications were immediate and obvious. American bomber formations flying at 25,000 to 30,000 feet operated in an altitude band where P-38 escorts held decisive performance advantage over Luftwaffe interceptors. Lurk dove from altitude to test high-speed handling and discovered another unpleasant surprise. The P-38 accelerated smoothly past 400 miles per hour, past 450, approaching 500 miles per hour in a steep dive. German fighters experiencing compressibility effects at these speeds became difficult or impossible to control as airflow over control surfaces approached supersonic velocities. The Lightning's controls stiffened but remained effective throughout the dive. Recovery required significant physical strength but was entirely manageable. American pilots in trouble at high altitude could simply push over into a dive and accelerate to speeds where German pursuers either broke off or lost control trying to follow. The concentrated nose armament revealed its advantages during test firing exercises conducted at Recklin's gunnery range. One Hispano M2 20mm cannon with 150 rounds flanked by 4 Browning M2.50 caliber machine guns with 500 rounds each, all mounted in the nose and firing directly forward without synchronization gear, created a cone of fire that was simply devastating to any target. German fighters with wing-mounted weapons suffered convergence problems where guns were harmonized to intersect at specific ranges. At distances closer or farther than harmonization range, shot patterns spread and effectiveness declined dramatically. The P-38's nose mounting eliminated this problem entirely. Every round fired traveled on a parallel path directly where the pilot aimed. Tests demonstrated that even brief firing bursts delivered concentrated firepower sufficient to destroy or seriously damage targets. But the real education began when German engineers commenced detailed teardown examination according to standard Rechlin evaluation procedures. They photographed every component. They measured every dimension. They weighed every assembly. They tested every system under varying conditions. What they discovered during systematic disassembly troubled engineers who had spent the previous 2 years learning to design around critical material shortages and manufacturing limitations. The Allison V1710 engines used forged aluminum alloy crankcases, sodium-cooled exhaust valves for thermal management, high-grade steel alloy crankshafts, and precision bearings throughout. Every component showed evidence of precision manufacturing to tolerances that German industry achieved only on experimental prototypes, never in mass production. Surface finishes were consistently excellent. Materials showed no evidence of substitution or compromise. The engines had been built exactly as designers intended, using all specified materials, without the desperate improvisations forced on German manufacturers by Allied strategic bombing and raw material shortages. The turbocharger systems, one per engine, represented technology German engineers understood theoretically but had never successfully implemented in production aircraft. Exhaust gases were routed through heavily insulated pipes to turbine units mounted in the tail booms. These turbines, spinning at tremendous speeds driven by hot exhaust, drove centrifugal compressors forcing additional air into engines. Intercoolers reduced compressed air temperature, increasing density and preventing destructive detonation. Automatic regulators controlled boost pressure and turbine speed without requiring constant pilot intervention. The entire system demanded exotic high-temperature alloys for turbine blades, precision manufacturing for rotating components, and reliable control systems functioning under extreme conditions. Germany had conducted experimental programs exploring similar approaches. Implementation in mass-produced combat aircraft had proven impossible given material shortages and manufacturing degradation caused by strategic bombing. The Americans had not only solved all technical problems but installed complete systems as standard equipment on thousands of aircraft. This casual implementation of advanced technology as routine production equipment revealed industrial capacity German engineers found difficult to fully comprehend. The flight control system demonstrated American willingness to accept additional weight and complexity in exchange for improved pilot control. Cables, pulleys, and bell cranks connecting control stick and rudder pedals to control surfaces were duplicated for redundancy. If primary control runs were damaged, backup systems provided continued controllability. Armor protection surrounded critical hydraulic components. The philosophy differed fundamentally from German approach, which minimized weight and complexity while accepting higher vulnerability. American designers assumed damage was inevitable and engineered for graceful degradation rather than catastrophic failure. Fuel system complexity astounded German analysts. Multiple self-sealing tanks distributed throughout the airframe were interconnected through valves and transfer pumps providing automatic fuel management. German fighters typically used simple gravity-fed systems from fuselage tanks, sometimes with small wing tanks requiring manual fuel management to maintain proper center of gravity. The P-38's automated fuel system maintained balance without pilot intervention while providing greater total capacity and better survivability when individual tanks were damaged. But automated systems required electrical pumps, solenoid valves, quantity gauges, and control logic. Every additional component introduced potential failure modes. The American solution was characteristically direct: build every component to higher reliability standards and install backup systems. The approach worked but required manufacturing capability and quality control that German industry could no longer consistently achieve. The radio installation compared favorably to anything in German service. The SCR 522 command radio provided clear air-to-air and air-to-ground communication with range and clarity exceeding German equivalents. An SCR 695 identification friend or foe system automatically identified friendly aircraft to ground controllers. German radio systems suffered persistent interference problems and limited range. American engineers had apparently solved these challenges through superior component design and better electromagnetic shielding. Testing revealed the radios functioned flawlessly even when other aircraft systems were damaged, suggesting careful attention to electromagnetic compatibility and physical protection. Perhaps most revealing was the comprehensive electrical system powering numerous accessories. Generators on each engine charged a 24-volt electrical system supplying power to radios, instruments, fuel pumps, landing gear motors, flap motors, gun charging systems, gun sight, cockpit heating, and navigation lights. German fighters used minimal electrical systems to reduce weight and complexity. The P-38 embraced electrical power for nearly every function, trading increased complexity for reduced pilot workload and improved capability. The philosophy assumed that reliable electrical components could be manufactured in quantity, that pilots should focus on tactics rather than systems management, and that weight penalties were acceptable prices for improved effectiveness. The detailed technical reports compiled at Rechlin and distributed through Luftwaffe intelligence channels documented every advantage and disadvantage with professional thoroughness. The P-38 showed clear superiority in high-altitude performance, concentrated firepower, redundant systems, pilot workload reduction, and damage tolerance. It demonstrated inferior qualities in roll rate at lower speeds, radius of turn at medium altitudes, and single-engine handling characteristics. The tactical recommendations were straightforward. Engage Lightnings below 15,000 feet where German fighters maintained maneuverability advantage. Avoid diving disengagements where the P-38 could accelerate beyond pursuit. Attack from below and behind where the twin-boom configuration created blind spots. Press attacks aggressively because the rugged Lightning absorbed damage and continued fighting. But tactical advice, however professionally developed, could not address the fundamental strategic reality the captured Lightning represented. Germany was attempting to fight an industrial war with insufficient industrial foundation. Every technical advantage German fighters possessed, every tactical innovation German pilots developed, proved increasingly irrelevant against opponents who replaced losses faster than Germans could inflict them. American production of the P-38 Lightning alone totaled 10,037 aircraft. Lockheed simultaneously produced these complex twin-engine fighters while American industry also manufactured P-47 Thunderbolts, P-51 Mustangs, P-61 Black Widows, and numerous other types. Total American fighter production exceeded 79,000 aircraft during the war. Germany produced approximately 47,000 fighters of all types during the entire conflict. The comparison extended beyond simple quantity. American aircraft reflected design priorities that accepted weight, complexity, and cost in exchange for capability, survivability, and reduced pilot workload. German aircraft increasingly reflected desperate attempts to extract maximum performance from minimum resources using minimum manufacturing time. Late-war German fighters incorporated wood components as aluminum became scarce, simplified systems as skilled labor disappeared, and eliminated accessories as production priorities shifted toward quantity over quality. American aircraft showed no such compromises. Every P-38 examined at Rechlin had been built exactly as designed, using specified materials, without substitutions forced by scarcity. The industrial infrastructure supporting American aviation production operated at scales German planners found difficult to conceptualize. The Aluminum Company of America alone produced more aluminum than Germany's entire aluminum industry. Individual American steel plants outproduced the Ruhr industrial region. Machine tool production allowed American industry to supply not only domestic requirements but also substantial quantities to British and Soviet allies. Even the logistics system supporting combat operations demonstrated overwhelming material advantage. American fighters operated with unlimited fuel, abundant ammunition, plentiful spare parts, and rapid replacement of combat losses. German fighters by 1944 faced chronic fuel shortages that limited training and operations, ammunition shortages that restricted gunnery practice, spare parts shortages that grounded aircraft awaiting repairs, and pilot shortages as training programs collapsed under fuel limitations. The captured P-38 eventually joined the Circus Rosarius demonstration unit, traveling to frontline bases throughout occupied Europe, allowing German pilots to examine Allied aircraft firsthand. The demonstrations served educational and psychological purposes. Pilots learned recognition features and combat characteristics of enemy aircraft. They also confronted physical evidence that Allied equipment frequently surpassed their own in critical capabilities. Post-war interviews with Luftwaffe pilots who attended these demonstrations revealed the demoralizing impact of seeing captured American and British aircraft capabilities demonstrated directly. The strategic bombing campaign provided brutal context for the intelligence gathered from captured aircraft. American heavy bombers, escorted by P-38 Lightnings, P-47 Thunderbolts, and P-51 Mustangs, systematically destroyed German industrial capacity throughout 1944. Synthetic fuel plants, ball-bearing factories, aircraft production facilities, and transportation infrastructure all suffered devastating attacks that progressively degraded German military capability. The fighter escorts that made deep penetration raids viable operated at altitudes and ranges where German interceptors fought at increasing disadvantage. By late 1944, German fighter units faced impossible mathematics. They needed to shoot down more bombers than reached targets to reduce bombing effectiveness, but escort fighters prevented interceptors from reaching bomber formations without first fighting through screening forces. The escorts held altitude advantage, numerical advantage, and increasingly tactical advantage as German pilot quality declined with compressed training. Lieutenant Albert Freeman, whose navigation error had delivered an intact P-38 to German intelligence, spent the remainder of the war at Stalag Luft III, the notorious prisoner of war camp that had been the site of the Great Escape earlier in 1944. He endured the brutal forced march westward when Soviet forces advanced in January 1945, a winter evacuation that killed numerous prisoners. Freeman survived, was liberated by Allied forces in April 1945, and returned to the United States. His aircraft, examined thoroughly at Rechlin and flown extensively by Circus Rosarius demonstration pilots, was recovered by American forces in May 1945 among collections of captured Allied equipment. Post-war evaluation by American technical intelligence teams focused more on assessing German evaluation procedures than on learning anything new about the P-38, which had been in American service for years. Hans Werner Lerck survived the war with his extraordinary safety record intact. His detailed memoirs, published decades later, provide invaluable first-hand accounts of Luftwaffe captured aircraft evaluation programs. His professional assessment of Allied aviation technology, delivered without nationalist bias or face-saving excuses, documents German recognition that they faced not merely quantitative disadvantage but qualitative inferiority in critical performance areas. Lerck's post-war cooperation with Allied intelligence services reflected professional aviator community bonds that transcended wartime national boundaries. The broader lesson revealed through systematic examination of Freeman's P-38 extended far beyond the specific technical characteristics of one aircraft type. The Lightning demonstrated American design philosophy that prioritized absolute capability over elegant efficiency, comprehensive systems over minimal complexity, and abundant resources over careful optimization. These priorities, implemented with industrial capacity exceeding all other major powers combined, produced weapons systems that outclassed German equivalents in aggregate combat effectiveness even when German designs showed superior individual characteristics in isolated parameters. Every category of captured American equipment documented the same fundamental pattern. The Boeing B-17 Flying Fortress bomber, with 4 turbocharged Wright Cyclone engines, represented strategic bombing capability Germany never achieved despite producing excellent medium bombers. The North American P-51 Mustang, combining American airframe engineering with British Rolls-Royce Merlin engine technology, created arguably the finest all-around piston fighter of the entire war. The Republic P-47 Thunderbolt demonstrated American willingness to build fighters larger and heavier than some twin-engine aircraft while achieving performance through overwhelming power rather than aerodynamic refinement. Each aircraft type reflected the same approach: solve problems through superior engineering backed by unlimited industrial capacity rather than through clever optimization constrained by resource scarcity. German technical intelligence reports compiled from captured aircraft evaluation programs documented these realities with scientific objectivity. The reports were professionally thorough, technically sophisticated, and strategically irrelevant. Understanding American capabilities did not provide Germany with the aluminum, steel, high-octane fuel, rare earth elements, machine tools, skilled workers, undamaged factories, and functioning logistics networks required to compete industrially. Knowledge without resources proved powerless to change outcomes already determined by industrial mathematics. The P-38 Lightning served throughout the war in every theater, achieving particular success in the Pacific where its range, twin-engine reliability over water, and heavy firepower proved ideally suited to vast oceanic distances and Japanese aircraft encountered. In Europe, the Lightning carved out specialized roles in photo reconnaissance and as bomber escort despite being gradually supplanted by P-51 Mustangs in the long-range escort mission. Lightnings destroyed more Japanese aircraft than any other Army Air Force fighter type, including the mission that killed Admiral Yamamoto when P-38s intercepted his transport aircraft based on decoded intelligence. The concentrated nose armament that German engineers examined so carefully at Rechlin proved devastatingly effective against Japanese bombers and fighters. Production statistics told their own story about industrial warfare in the 20th century. Lockheed produced 10,037 P-38 Lightnings while simultaneously manufacturing numerous other aircraft types. This represented complex twin-engine fighters built to demanding specifications without compromises. Germany produced 6,000 Messerschmitt Bf 110 twin-engine fighters, 6,150 Messerschmitt Me 410 heavy fighters, and approximately 900 examples of various other twin-engine fighter types, totaling roughly 13,000 twin-engine fighters of all types during the entire war. American production of one advanced twin-engine fighter type approached total German production of all twin-engine fighters combined. The quality comparison paralleled the quantity disparity. American aircraft in 1944 reflected continuous improvement based on combat experience, with modifications and upgrades implemented systematically across production runs. German aircraft increasingly reflected desperate attempts to maintain production despite collapsing infrastructure, with quality control failures, substitute materials, and simplified systems degrading performance and reliability. An American pilot climbing into a factory-fresh P-38 in mid-1944 received an aircraft built to exact specifications using premium materials. A German pilot receiving a factory-fresh Bf-109G in the same period might find wood-tail surfaces replacing aluminum originals, instruments missing entirely, radios non-functional, and engine reliability questionable due to forced labor assembly. The psychological dimension of industrial disparity proved as destructive as material losses. German pilots increasingly reported feeling overwhelmed by endless streams of capable enemy aircraft. Combat became less about achieving victory through skill and more about surviving through luck. No matter how many Allied aircraft German pilots shot down, more appeared the next day and the day after. The numerical odds worsened continuously as German losses exceeded replacement rates while Allied losses were replaced within days. Veteran pilots died or were captured, their experience and skill lost permanently, replaced by inadequately trained novices with minimal flight hours and insufficient gunnery practice due to fuel shortages. The knowledge that enemy equipment often exceeded their own, delivered in overwhelming quantities, supported by superior logistics, and flown by adequately trained pilots who were rapidly replaced when lost, created pervasive demoralization throughout German fighter forces during 1944 and 1945. The captured P-38 Lightning served as physical evidence of these realities that propaganda could not disguise. German pilots could examine the aircraft directly, noting sophisticated systems, quality materials, and comprehensive capabilities. The Lightning was not some wonder weapon or revolutionary technology. It was simply an excellent twin-engine fighter, properly designed for its mission, adequately powered through turbocharger technology, well armed with concentrated firepower, appropriately protected with armor and redundant systems, and manufactured in quantities sufficient to overwhelm opposition through systematic application of material superiority. The final irony was that German engineers learned these lessons thoroughly, documented them professionally, grasped the strategic implications completely, yet could never apply knowledge gained. Understanding American industrial superiority did not grant Germany the resources, infrastructure, or time needed to respond effectively. By the time Freeman's P-38 was being meticulously examined at Rechlin in August 1944, Paris was weeks from liberation, Soviet forces were approaching German borders from the east, and the strategic bombing campaign had degraded German industrial capacity beyond recovery. The lessons arrived too late to matter. The outcome had been determined not by tactical excellence or technological innovation but by industrial mathematics that no amount of German engineering skill could overcome. The Republic P-38 Lightning, examined in detail by German engineers at Rechlin, proved the final truth about industrialized warfare in the 20th century. Adequate capability produced in overwhelming quantities through competent engineering and supported by vast industrial infrastructure defeated technical excellence constrained by insufficient resources. The most powerful element in America's arsenal was not any individual weapon system, however impressive, but the complete industrial ecosystem that could simultaneously conceive, design, develop, test, produce, and logistically support thousands of complex weapons systems while continuously improving designs based on combat feedback. German engineers measured this reality precisely, documented it professionally, and reported it accurately through command channels. Knowledge arrived too late. By the time the lessons were learned, industrial mathematics had already determined the war's outcome. Material abundance had defeated constrained excellence. The age of industrial warfare had announced its verdict, and no amount of tactical brilliance could appeal the judgment.